In this video, which will be our last on rotational motion, we'll look at rotational kinetic energy and how we can use conservation of energy to solve problems where we have objects rolling, such as our hoop or disc rolling down an incline. We'll also look at angular momentum. Let's start out by looking at rotational kinetic energy. We know that linear kinetic energy is equal to 1/2 mv squared. We've also learned that the rotational equivalent of mass is moment of inertia, and the rotational equivalent of linear velocity is angular velocity. And therefore, it won't surprise you to learn that rotational kinetic energy is equal to 1/2 I omega squared. So instead of mass and velocity, we have moment of inertia and angular velocity. Let's just check the units to make sure that this really is an energy. We know that energy should have units of joules, and so let's make sure it does. The units of moment of inertia, remember, are kilogram meters squared. We know the units of omega are radians per second, and we've got to square that. So we get radians squared per second squared. Remember, we can always get rid of radians because it's not a real unit. It's really just representing a ratio of two lengths. And so we end up with kilogram meters squared per second squared. Well, you'll notice that that's exactly the same as we get up here, kilogram meters squared per second squared, and that is the definition of a joule. So we can see that that formula for rotational kinetic energy does give us an energy. Before we can look at problems such as how fast will a disk be going at the bottom of an incline after it rolls down, we have to understand the relationship between linear velocity and angular velocity for an object that's rolling without slipping. So if an object is rolling without slipping, there is a definite relationship between the linear velocity of the center of the object and the angular velocity about the center. That's what we need to determine. So in other words, what is the relationship between that velocity and the angular velocity about the center of the axis? The easiest way to think about this is just think that as that tire is rolling along, its linear velocity is just the distance that it travels divided by the amount of time that it takes to travel that distance. And if we think about that tire rotating, let's think about what distance does the tire move in one rotation? Well, it simply travels a distance of 2 pi r, the circumference of the tire, in one period. Now, the radius, capital R, is just the radius of the tire. So one revolution, the tire will travel that linear distance of 2 pi r. Well, we know that 2 pi divided by the period is omega. And so our relationship is that the linear velocity of the center of the tire is equal to the angular velocity about the center times the radius of the tire. Now, you may look at that formula and say, well, didn't we have the formula V equals omega r earlier? We did, but it had a completely different meaning. Remember, what that formula refers to is that if I've got an object that's rotating about this point with some angular velocity omega, if I want to know the linear velocity of some point on that object, I can use that formula to find it. So in other words, if this object is spinning in this direction, we're talking about what is the velocity, the tangential velocity, a distance r from the center. Okay? Here, we're talking about the velocity of the center of the tire relative to the ground. Okay? Sometimes we refer to that as the center of mass velocity. The key thing then we have to understand is that when an object is rolling without slipping, the linear velocity and the angular velocity are not independent of each other, but are related by this formula. Notice, by the way, if you're doing a burnout in a parking lot and spinning your tires, this isn't relevant. This is only true if your tire is rolling without slipping. Okay, so let's see how we can combine all this information to solve a problem like this. How do we actually figure out how fast this object would be going as it gets to the bottom of the incline? Well, basically, it's just conservation of energy. We know that the work energy principle tells us that delta K plus delta U equals WNC. Now, the first thing that I want to think about is, do we have any non-conservative forces present as this object rolls down the incline without slipping? Well, first of all, is there friction? The answer is there definitely is friction, because if there were no friction, the object wouldn't roll, right? It would just slide. So there is friction in the problem, and that might make you think that there is work being done by friction. But the friction does no work. And the question is, why is it that the friction doesn't do work? Remember that work is F delta R cosine theta. In order for a force to do work, there has to be motion along the direction of the force. That's the key thing. Well, when an object is rolling without slipping, so if I look at this object, the force of friction is in that direction. But there's no relative motion here. That's what we mean by rolling without slipping. So delta R is 0. And therefore, even though there is a non-conservative force present, the only thing that force is doing is exerting a torque on the wheel that makes it turn. But it's not doing any work. And therefore, the work done by non-conservative forces is 0. So in order to figure out a problem like this, then, the only thing that's different than when we did this problem before with an object sliding down an incline is that delta K is now going to be 4 terms. In other words, the final translational kinetic energy plus the final rotational kinetic energy, and then minus the initial values of both of those. So we have both translational kinetic energy and rotational kinetic energy present in the problem. Let's do an example problem to see how this works. A disk starts at the top of a ramp at a height h. So we'll start out with our disk at an initial height h. What will the velocity of the disk be at the bottom of the incline? So it starts at rest, so we know that v naught is equal to 0. What we're looking for is, what is the velocity v at the bottom? We know that we're going to use conservation of energy. Delta K plus delta U equals WNC. And as we just discussed, although there is friction, because if there weren't friction, the object wouldn't roll, that friction doesn't do any work because the object is not sliding along in the direction of the friction, or opposite the direction of the friction. So the work is 0. The next step then is I'm just going to write out every term. In other words, delta K is now both the final kinetic energy minus the initial kinetic energy plus the final rotational kinetic energy minus the initial rotational kinetic energy. So again, delta K is now 4 terms. Delta U is just what it has been before, mgy minus mgy naught. And as we said, there's no work done by non-conservative forces, so that's equal to 0. Notice that in my problem here, y naught is just going to be equal to h, and I'm going to set my origin at the bottom so that y is equal to 0. Okay, so what's the next step? The next step is where I'm just going to cancel anything out that I know is 0. We know that the initial kinetic energy was 0. It wasn't moving yet. Therefore, it wasn't rotating yet either. So both of our initial kinetic energy terms are 0. And because I've set my origin at the bottom of the ramp, my final gravitational potential energy is equal to 0. So that leaves me with 1/2 mv squared plus 1/2 I omega squared is equal to mgy naught. And I want to just pause here for a second and think about the significance of that equation. Notice that what it's telling us is that initial potential energy that the object had at the height of the ramp has now been split into two types of kinetic energy. So one of the things you'll notice is that an object will roll down an incline. When an object rolls down an incline, it will be going slower at the bottom than an object that just slid down without friction. Because not only does the gravitational potential energy go into translational kinetic energy, some of it also has to go into rotational kinetic energy. The next step is to remember that I and omega are not independent of m and v. I just depends on what object it is that we're looking at. So we need to know what is the moment of inertia for the object. In this case, it's a disk, so it's 1/2 mr squared. And by the way, that should just be a small m there. The reason we use capital R there is, again, simply that we mean the radius of the object. Okay, we also know that omega is not independent of v. We just talked about the fact that when an object rolls without slipping, v is equal to omega times capital R, where again that's the radius of the object. So the next step that we do is we rewrite I and omega in terms of m and v. So I have 1/2 mv squared plus 1/2 times I, which is 1/2 mr squared, times omega, but omega, you'll notice, is v over r. So I'm going to put in v squared over r squared, and that has to equal mgy naught. Now at this point, we can see some things are going to cancel out. Notice the r squareds cancel out. And that's good, because we've got to have energy there. It's got to be mv squared when everything is all said and done. The other thing that I can do at this point is I can get rid of mass, because every term has an m in it now. So I get 1/2 v squared plus 1/4 v squared is equal to g. And since y naught is equal to h, I'll just put in the h. And therefore I get 3/4 v squared is equal to gh, or v is equal to the square root of 4/3 gh. And that's my answer. One of the things I mentioned previously that I just want to point out is that sliding without friction is faster than rolling. Because if you remember, and you could just quickly work it out again here, you'll notice if the object is just sliding with no friction, we don't have that term. And what we end up with for our answer is that v is equal to the square root of 2gh. Okay? So sliding without friction is faster than rolling. And that makes sense because if an object is rolling, some of that gravitational potential energy has to go into rolling energy, rotational kinetic energy. Not all of it can go into translational kinetic energy. Here's a problem that I want you to try to do completely on your own, and then I'll go through the solution with you. So we've got a sphere, and our sphere is going to roll down this incline. When it gets to the bottom, it's going to go straight off the table. And what I want to know is, where is the object going to land? Well, you'll notice that this is a two-step problem. Because it's a sphere, I've given you the moment of inertia for a sphere. So I want you to figure out what is the velocity at the bottom of the ramp. Well, then that's going to be your initial velocity for the projectile motion part of the problem. So this is a nice review of a simple projectile motion problem as well as a rotation problem. Go ahead, pause the video, and see if you can figure out what the final position is going to be. So let's go ahead and figure it out together. The first thing that I need to figure out is what is the velocity going to be at the bottom of the ramp. Well, this is very similar to the example we just did before, so let's go through it again. Delta K plus delta U equals WNC, always starting at the work energy principle. Then, as we've talked about, the work done by friction is 0, and so I can get rid of that. And delta K simply represents the change in linear kinetic energy as well as the change in rotational kinetic energy. And then we have our change in gravitational potential energy, mgy minus mgy naught, and that equals 0. Once again, in this case, my object was starting from rest, and therefore there was no initial kinetic energy, no initial rotational kinetic energy, and for the first part of the problem, that's going to be my origin, and therefore the final potential energy is 0. Therefore, I get 1/2 mv squared plus 1/2 I omega squared is equal to mgy naught. At this point, remember, we need to write I and omega in terms of m and v. So 1/2 mv squared plus 1/2 times 2 mr squared over 5. Remember, omega is v over r, so omega squared would be v squared over r squared. That's equal to mg y naught. Now every term has an m in it, so I can get rid of all of the m's. This r squared cancels with this r squared, and I get 1/2 v squared plus 1/5 v squared is equal to gy naught. Doing some algebra, adding 1/2 and 1/5, I get 7/10. So 7/10 v squared is equal to gy naught, or v is equal to the square root of 10 over 7 times gy naught. If you put in the numbers that I gave you, you should get 1.94 meters per second. So that's the velocity that our object has when it leaves the table. Now, for the kinematics part of the problem, I'm not going to review that fully. I'm just going to give you the answer and let you go and review it if you need to. We know that since v naught for the kinematics part of the problem is only in the x direction, so that's vx naught, what we have is vx naught is 1.94 meters per second, and vy naught is equal to 0. You should be able to show, starting with your two-dimensional kinematic equations, that t ends up being equal to the square root of 2y naught over g. And when you plug in the values, you should get 0.43 seconds for that. And then figuring out the final position in the x direction from the edge of the table here is just x is equal to x naught plus vx naught t, and you should be able to show that it will land a distance of 0.84 meters from the edge of the table. Let's talk about angular momentum as our last topic. We know that linear momentum is m times v, and so it's not going to surprise you that angular momentum is defined as I times omega, because again, we know that the rotational equivalent of mass is moment of inertia, and the rotational equivalent of linear velocity is angular velocity. We use capital L to represent angular momentum. Let's take a look at the units for angular momentum. You'll notice that the units are kilogram meters squared per second, and again, that's because moment of inertia has units of kilogram meters squared, and omega has radians per second. And again, we can just get rid of the radians anytime we want to, and so we get kilogram meter squared per second. Now, why is angular momentum an important quantity, and where does the concept come from? Remember where linear momentum came from. When Newton wrote his second law, he actually wrote it in terms of the momentum. He said the net force is equal to the rate of change of the momentum with respect to time. And that's where the definition of momentum comes from. Remember that that means if you have a system like objects that are about to collide and there are no external forces acting, it means that the net change of momentum has to be zero. And that's where conservation of momentum came from that we looked at when we looked at things like collisions and explosions. Well, conservation of angular momentum comes from Newton's second law for rotation, something that we talked about earlier, that the net torque on an object is equal to its moment of inertia times its angular acceleration. Well, notice that really, although we wrote it that way, more generally, the net torque is equal to the rate of change of the angular momentum, because you'll notice if you take the derivative of this, you get back to I alpha. So what does this tell us? It tells us that if there's no net torque acting on an object or on a system, then the angular momentum has to stay constant. Let's look at the classic example of this, which is a figure skater. So I'm sure you've all seen this at some point, where we've got a figure skater, and my drawing of a figure skater is not going to be great here, but our figure skater has their arms out and they're doing a spin. What happens as our figure skater brings their arms in? Well, I'm sure you've all seen that and you know what happens. What happens is the angular velocity of the skater increases. Well, that's just conservation of angular momentum. In other words, the angular momentum before our skater brings in their arms and after has to be the same because there's no external torques acting. The person is just bringing their arms in themselves. And so what we find then is that if we look at the moment of inertia times the angular velocity before the skater pulls in their arms, that's got to be equal to the moment of inertia times the angular velocity after the skater brings in their arms. So let's look at this problem. A figure skater is initially spinning at 0.5 revolutions per second. She pulls in her arms and legs and speeds up to 3 revolutions per second. If her initial moment of inertia was 4.6 kilogram meters squared, what was her final moment of inertia? Well, first of all, we know it's going to decrease, otherwise she wouldn't speed up. So what is it? Well, we're just going to use this formula. Notice, by the way, we weren't given angular velocity, we were given frequency. But that's okay because we hopefully remember that angular velocity is equal to 2 pi times the frequency. So I could rewrite this as I times 2 pi initial frequency is equal to IF times 2 pi times the final frequency. And we can see that even if you had kind of not realized that I gave you frequency, not angular velocity, it would have turned out okay because the 2 pi's are going to cancel out. And therefore what we get is that her final moment of inertia is just going to be her initial moment of inertia times her initial frequency divided by her final frequency. If you plug in the values, you get 0.77 kilogram meters squared. So that's a simple example of conservation of angular momentum. I want to go back to something that we talked about a number of videos ago, which was one of Kepler's laws, which talked about a planet sweeping out equal areas in equal times. And what we said about that was that when the planet is closer to the sun, it's moving faster than when the planet is farther away from the sun. We can now understand that as an example of conservation of angular momentum. When the planet is out here, because it's farther away from the sun, its moment of inertia about the sun is bigger, and therefore its angular velocity has to be smaller. When the planet is closer to the sun, since its distance is closer, its moment of inertia relative to the sun is smaller, and therefore it has to be going faster. Okay, that's the end of our study of rotation.